Hi everyone, this is our Eclipse video on Section 4.4. You might recall that we've already begun this section and have covered, maybe a third of it. So the goal here in the video is to review that third that we've covered and then continue breaking new ground and then finish the section. Recall that the main goals of this section are to verify the extreme value theorem, which you remember is a very important theorem in calculus, and then also to introduce a new notion, that is, of uniform continuity. The last time we were together, we proved this important theorem in analysis that says that if you have a continuous function on a compact set, then the image of that set under the function is also compact. One can view this theorem as sort of a maturer version of the extreme value theorem. On this slide, we have a more recognizable version of the extreme value theorem given as a corollary to the previous theorem. It says that if you've got a continuous function on a compact set, then that function must attain an absolute maximum and an absolute minimum on that set. Remember that we discussed the proof of this theorem the last time we were together. Now that we've dispatched with the extreme value theorem, we move on to this notion of uniform continuity. So you might remember that for ordinary continuity of a function at a point C in the domain, the name of the game is to produce the appropriate value of delta that will work. So that's usually what we want to do. And then the question is, what does that delta depend upon? Well, it depends on the function and it depends on epsilon, certainly, or usually it does. And it also often depends on the point in question in the domain. Now, in uniform continuity, we require that our choice of delta work for every choice of point in the domain. So it's independent of where we are in the domain. And if you want a graphical sort of view of this, you can look here at this picture. The idea is that if you're given a tolerance epsilon, you want to select a delta and then produce a little cylinder of radius epsilon and length delta that you could slide along the graph without ever having the graph touch the, either the bottom or the top or the bottom of the cylinder. The last time we were together, we made it through this first example of uniform continuity. So we're asserting here that the squaring function is uniformly continuous on the closed interval from 0 to 1. So anyway, someone hands us an epsilon, and then we go off somewhere down into a basement maybe, and we produce a value of delta that we believe is going to work. So we claim that delta equaling epsilon over 2 will work. And so we claim that whenever x minus y is less than delta in absolute value, that x squared minus y squared will be less than epsilon. So we follow this chain of inequalities. We factor the difference of squares into x plus y and x minus y. Now, remember that if x and y are both in the unit interval from 0 to 1, then x plus y is less than or equal to 2. So that explains this inequality here. And then x minus y is less than delta, which in turn is equal to epsilon over 2. And so when we multiply all of this stuff together, we wind up getting epsilon. And so whenever x minus y is less than delta in absolute value, we have verified that x squared minus y squared will be less than epsilon in absolute value. And so that's what we need to do to show that the squaring function is uniformly continuous. So one thing that you might do is stop the video and see if you can reproduce this argument where we look at the squaring function on the closed interval from 0 to 3. Not every continuous function turns out to be uniformly continuous. Now, if we're going to show that a function is not uniformly continuous, then we need to know what it is exactly that we need to show. So at the top of the slide here, we're just reviewing what it means for a function to be uniformly continuous. And then below, in two separate statements that are equivalent, we have statements of what it means for a function to not be uniformly continuous. So one of the statements, the first one, is in terms of epsilons and deltas. The second statement is in terms of sequences. So you might take a moment here and look pretty carefully at both of these statements. Now you might be wondering how we took the statement of uniform continuity, which appears at the top of the previous slide, and negated it to obtain the statements, the two statements that follow it on the previous slide. Well, it turns out that we can do that negation using symbolic logic. Those of you who are taking Math 470 and are students at Ball State, you might recall learning some things about symbolic logic in Math 215. And so we're going to use some of those things that you learned there to negate the statement of uniform continuity. Okay, so the first thing is we have this top line. And what we are attempting to do here, what this is conveying, is that we are going to negate the statement that lies to the right of that symbol. And that statement is, for all epsilon, there exists delta, such that for all x and for all y, if x minus y is less than delta in absolute value, then f of x minus f of y is less than epsilon in absolute value. So this thing out in front here indicates that we wish to negate that uniform continuity statement. Now our first step doesn't involve doing anything with this negation at all. It has to do with reformulating the if-then statement that's inside the brackets. So you might remember that if P then Q is logically equivalent to not P or Q. So that logical equivalence is what you might remember as being called implication, and that's what we're applying in moving from this first line down to this second line. So that is what's being applied within the brackets. Now to go from the second line to the third line, what we're doing is we're taking this negation on the outside and we're moving it through the quantifiers. And you might recall that when you move a negation sign past a quantifier, it changes the quantifier either from a for all to a there exists or from a there exists to a for all. And so that's how we've gotten to this third line here. Okay, now what we want to do is we want to take this negation and we want to move it inside the bracket statement. Now to do that, we use something called De Morgan's rule. And so De Morgan says that if you negate an or statement, like P or Q, then that is equivalent to saying not P and not Q. And so here, in going from this line to that line, we're applying De Morgan's rule. And once we've done that, we're sort of done with our negation. And now all that's left for us to do is read off what we have. And you see that when we read off, we get there exists an epsilon bigger than 0, such that for any delta bigger than 0, there exists x and y such that x minus y is less than delta in absolute value, and however, absolute f of x minus f of y is bigger than or equal to epsilon. Okay, so you should compare this with the first negation statement that appears on the previous slide. So now that our little lesson on symbolic logic is behind us, let's actually show that a particular function is not uniformly continuous. So here, once again, we're looking at the squaring function, but this time, instead of looking at this function defined on a bounded closed interval, we're going to look at it on the interval from 0 to infinity. So our method of proof here involves the sequential characterization of the negation of uniform continuity. So this is the characterization that was given a couple of slides ago. So we're going to take two sequences, xn and yn, both living in the domain, where xn is n plus 1 over n, and yn is just n. And the epsilon we're going to select here is 2. So observe that these two sequences, the difference, xn minus yn, tends to 0. But now when we apply the function and look at the difference, we look at xn squared minus yn squared, that number is always bigger than or equal to 2. And so from this sequential characterization of the negation of uniform continuity, we can conclude that this function, the squaring function, fails to be uniformly continuous on the interval from 0 to infinity. Earlier, when we were together discussing Section 4.4, we pointed out that uniform continuity is a stronger notion than continuity. That is, that any uniformly continuous function will be continuous. And evidently, the opposite statement is not true, right? Because we just saw that the squaring function on the interval from 0 to infinity, which is a continuous function, fails to be uniformly continuous. However, if you put a continuous function together with a compact set, that is, if our continuous function is defined on a compact set, then it turns out that the function is guaranteed to be uniformly continuous. So the proof here is by contradiction. We assume that f is not uniformly continuous. If that's true, then we can use that sequential characterization that we had a couple of slides ago to find a couple of sequences xn and yn in our domain, K, and we can select an epsilon bigger than 0 such that xn minus yn tends to 0, but when we apply the function values and subtract, we're always bigger than epsilon in absolute value. Now, because K is compact, you might remember that compactness means that if you're given a sequence in that set, then there must be a subsequence that converges in the set. So that means there must be a subsequence y sub n sub k of y sub n that converges to some y that's in K. But now, remember, xn minus yn goes to 0, and so that means that x sub n sub k minus y sub n sub k must tend to 0. And then by the algebraic limit theorem, that says that x sub n sub k tends to y also. Now, what does that mean? Well, we know that f is continuous, right? And so by the sequential characterization of continuity, y sub n sub k and x sub n sub k both converge to this y. And that means that when we apply our function, these two sequences of function values here, this one and that one, they both must converge to f of y. And so that means that the difference between these two must converge to 0, right? Because each of these individually is getting close to f of y, and when we subtract, we get something small. So that's a contradiction, because remember, f of x sub n minus f of y sub n were always supposed to be bigger than some epsilon naught. And so we've got a contradiction here, and that means that this function really is uniformly continuous. All right, our final slide is about a little splicing theorem that turns out to be useful when you're working on exercise 7. So the idea here is that if you've got a uniformly continuous function on a big interval from b to infinity, and just a plain old continuous function on the interval from 0 to b, then the function is uniformly continuous on the grand large interval from 0 to infinity. So let's see if we can snake our way through this, the proof of this. So we let epsilon greater than 0 be given, and of course the name of the game is to find a delta that's going to do what we want it to do. So anyway, since f is continuous on the interval from 0 to b, we know it's uniformly continuous there. And so we can pick a delta 1 so that if x and y are in that small interval and they're within delta 1 of each other, then the corresponding function values are within epsilon over 2 of each other. Okay, now we move up, turn our attention to the big interval. So likewise, we know f is uniformly continuous on this interval from b to infinity, so we can select a delta 2 so that if x and y are in the big interval and they're within delta 2 of each other, then the corresponding function values are within epsilon over 2 of each other. So now what we're going to do is we've got delta 1 and delta 2. We're going to pick delta here to be the minimum of those two. And now let's suppose we've got x and y in the grand large interval from 0 to infinity that are within delta with each other. Now, if both x and y are in this interval from b to infinity, then all is good, right? Because we know that this delta is less than or equal to delta 2, and so we're good. If both x and y are in the little interval from 0 to b, then we're good because our delta is less than or equal to delta 1. So really the only concern is when b is between x and y. Okay, so if b is between x and y, then both x minus b and y minus b, both of those in absolute value, both of these are less than x minus y, right? If b happens to be between x and y. So when that happens, we just make note that, both x and b either lie in 0b or they both lie in b to infinity, and the same for y and b. And then what you do is you just simply take your difference of function values here and you add and subtract f of b, and then we use the fact that both of these guys are less than delta if this guy is less than delta, to obtain that both of the differences of function values are less than epsilon over 2. And then we add them together, and that gives us epsilon.